Hi, I'd like to talk about a model for looking at the dynamics of a system using the lens of energy for systems that we consider to be energetically isolated systems. And we'll start by taking a look at systems without friction. We'll talk about friction in a later point. So, when something is isolated, it means that all forms of energy transmission equals zero. In addition to the total sort of forms of energy transmission equals zero. So our work is zero, our heat is zero. Mechanical waves, mass transfer, electrical transmission, electromagnetic radiation, all of those forms of energy transfer, which are all of the forms of energy transfer, equal zero. Now, if we ignore friction, when we take a look at the change in energy side, we'd have a change in kinetic energy, we'd have a change in potential energy, and we could have a change in internal energy. Now, one of the primary ways we change internal energy is through the frictional process. So if we don't have that, then it's incredibly difficult to change the internal energy of an isolated system. Now, we could still have objects colliding at near the speed of light and mass changing into energy, but we're going to ignore that. We're just going to say that everyday sort of normal physical problems we could solve by taking a look at a condition of the change in kinetic energy plus the change in potential energy equals zero if we have a scenario where we have no work, no heat, or the other four forms of energy transfer. So an example of that is pretty much taking a look at any kinematic problem. So say we wanted to drop a coin off the top of One World Trade Center tower. Well, the height of One World Trade Center is 1,776 feet, which happens to be 541.3 meters. And if we have an isolated system, we model it as an isolated system, we're ignoring the effects of air resistance. So what's going to happen then is that coin will have a change in kinetic energy, it'll have a change in potential energy, and from that, we should be able to come to a full understanding of the motion. Now, the change in kinetic energy is our final kinetic energy minus our initial kinetic energy. Just as our change in potential energy is our final potential energy minus our initial potential energy. So if we're looking at a falling object, then the only potential energy we need to consider here is the potential energy due to gravity. And if I rearrange this to have only positive terms, I add those two negative terms to the other side, then I have my final kinetic energy plus my final potential energy equals my initial kinetic energy plus my initial potential energy. And kinetic plus potential energy is what we refer to as our mechanical energy. So this is saying our final mechanical energy equals our initial mechanical energy. And the reason why we call the forces that give us potential energy conservative forces is because they are conserving this mechanical energy. So, if we start with the object in our hand at rest, that means its initial kinetic energy is going to be zero. And just before that object hits the ground, the final kinetic energy of that object would be 1/2 times its mass times its speed just before it hits the ground squared. Now, potential energy is based off an integral, and integrals are unique only to a constant of integration, which means with potential energy, you are free to pick zero potential energy to be wherever you want it to be. So if we're just dealing with gravity, I always like to take the lowest possible point in my system physically and set that point to be equal to zero potential energy. So for a coin falling towards the ground is zero potential energy, so at the top of the building, our potential energy will be the mass of the coin times the strength of gravity times the height of the building. So, my initial energy is just the mass times gravity times the height. My final energy is just 1/2 times the mass times the speed squared. So if I set those two energies equal to each other, the mass cancels out. I can multiply both sides by 2 so that the speed squared is 2 times gravity times the height, and the square root of that tells me the speed is going to be the square root of 2 times the strength of gravity, 9.8 meters per second squared, times the height of One World Trade Center, which the height is 1,776 feet, or in meters, 541.3 meters. So I multiply those pieces together and find the square root, and that would give me a speed of the coin just before hitting the ground of 103 meters per second, which is just about 230 miles per hour. Thanks for watching.